Let's move on to how Python interacts with the outside world through files. The most fundamental function for file operation is the open function. So the open function takes two arguments, the file name and mode. File name is simply the name or path of the file that you want to work with, and mode tells the Python what kind of operation you want to perform. So let's break down the different modes that are available in Python. So R stands for read mode, so it is the default one. If you try to open a file in read mode and it doesn't exist, Python will raise file not found error. A means append. It opens the file for writing, but unlike write mode, it won't delete what is already there. It will start writing at the end of the file. If the file doesn't exist, it creates one. W stands for write. This mode also creates a new file if one doesn't exist, but it completely overrides the file if it already exists. X stands for create. So this one is useful when you want to make sure you are not overwriting anything. It will create the file but throw an error if it already exists. Now in addition to these, you can specify whether the file is opened in text and binary mode. T is for text mode, which is the default, and it means Python will read and write human readable strings, especially encoded in UTF-8. B is a binary mode, which is used when working with non-text files such as the executables, audio and image files. So when you combine these, you might use RB for reading a binary file or WT for writing text explicitly, though the text is default. Once a file is open, you can read its contents using several built-in functions. Like read reads a specific number of characters from the current position in the file. If you do not pass any argument, it reads the entire file in one go. Read line method reads a single line from the file, that is everything from the current position up to the next new line character, that is \n. It is useful when you want to process file line by line. Read lines method reads all the remaining lines from the file and returns them as a list, where each element represents one line of text including the new line character at the end. These methods make file reading very flexible. You can read just what you need, whether a few characters, a single line or entire file. When we read data from a file, Python keeps the track of where we are inside that file using something called a file pointer. Each time we read or write, this pointer moves forward automatically. But sometimes we might want to move back and forth in the file. For example, maybe to reread something or skip certain paths. That's exactly where random access and seek function comes into play. So the syntax is simple, f.seek, and you pass offset and then second argument is from. Here offset is how many bytes you want to move, and from tells Python where to start counting from. There are three possible values for from. 0 means start counting from the beginning of the file, so f.seek 0,0 moves the pointer right back to the start. 1 means start counting from the current position. You can use positive or negative offsets here to move forward or backward. 2 means start counting from the end of the file. This is often used when you want to append data or inspect the end of the large files. The ability to reposition the file pointer gives us precise control over the file access, especially when dealing with binary files or when reading structured data in chunks. You can check the pointer's position using tell function. So seek works best with binaries or structured data where byte level control matters. In text mode, seek only works reliably with positions returned by tell because of text encoding. Up till now, we have been working with text files where Python reads and writes human readable strings like word, numbers in plain text form. But what if we want to work with raw binary data? For example, when saving images, videos or serialized numeric data. For that, Python provides a binary file handling mode such as WB for writing, RB for reading and AB for appending binary data. Let's look at an example. Here we open a file called file.bin using WB, which means write binary. Next we define a list of numbers that are 5, 10, 15, 20, 25. Now to write numeric data directly to a binary file, we just can't use write function on the list itself, because write expect a sequence of bytes, not integers. So we use the built-in byte array function to convert our list of integers into a sequence of byte values. Each number in the list becomes a single byte. For example, 5 becomes that pattern ending with 101. After that, write method stores these bytes into the file exactly as they are, no encoding, no formatting, just pure binary data. Finally, we close the file to ensure all data is saved properly. The resulting file, file.bin, now contains 5 bytes of data, 1 byte for each number in the array. So to summarize, writing to a binary file involves opening a file in binary mode, converting your data to a sequence of bytes, and using write to store it. This approach ensures that your data is preserved exactly as it is without any encoding or formatting changes. In Python, we can not only store text or byte, we can also store entire Python objects like dictionaries, lists, or even class instances. This process is known as object serialization, or in Python terms, pickling. Here's how it works. We start by importing the pickle module. When we define a dictionary called data, which contains keys, values, or even a list, in other words, complex data structure in Python. To save this object to a file, we open the file in binary write mode, WB, and call the function pickle.dump and pass data_nf. This function converts our Python object into a sequence of bytes, a serialized stream, and stores it inside the file. When we want to bring the object back, we open the same file in binary read mode, RB, and call pickle.load. This function deserializes the byte stream and reconstructs the same Python object in memory. The result is we can pick up where we are left off with the same data structure without needing to parse or re-enter it manually. In this example, we are learning how to read data from a text file and transform it into a useful numeric values. We begin by opening the file f1.txt in read mode. The function read loads the entire content as a string. Suppose the file contains text 45,67. Using the split comma method, we divide the string into parts where there is a comma, giving us a list of strings like 45 and 67 as entries. But notice these are still strings, not numbers. So we use a list comprehension to convert each element from a string to an integer. Now our list becomes a regular integer list with 46 and 67 element entries. Finally, we unpack the two lists into a separate variables x and y. This technique is useful when you know exactly how many values you expect to extract from the file. The output confirms the transformation from raw text to split strings to integers and finally to individual variables. So this is a common approach when dealing with comma separated data such as CSV files. So this simple example demonstrates Python's power in transforming the text file to structured list and to typed numeric values. You will use this same pattern often when dealing with text-based data files, logs, or CSV files.